Hi Chemistry, Mrs. KJ here, going over lesson 4.05, Properties of Ionic Compounds. Ionic compounds are formed by electrostatic attraction, which gives them their common properties. All right, what do we mean by electrostatic? Well, electro should make you think of electricity or electron. Okay, electrons. Electrons are negative. What are they attracted to? Positive protons. So the whole reason ionic compounds form is because of a positive and a negative charge being attracted to each other. In this lesson, you will learn about the properties of ionic compounds and how the ionic bond accounts for these properties. So, ionic bond is between a metal and a nonmetal. Anytime we talk about ionic compounds, what compound should be in your head? Table salt. And what is the chemical formula for table salt? NaCl. So you should always be thinking about NaCl, sodium chloride, table salt. So ionic bond. So that's the bond between the sodium and the chlorine to make sodium chloride table salt. That bond is very strong. That bond can dissolve in water to form a solution that conducts electricity. Goals for the lesson: identify the properties of ionic compounds, describe how metallic bonds formed, list and discuss some of the properties of ionic compounds, explain how the nature of the ionic bond accounts for various properties of ionic compounds, explain why ionic compounds are excellent conductors of electricity when they are dissolved in water. Not when they're solids, but only when they are dissolved in water. If you want the study guide, go ahead and log into the lesson and download it. Explore properties of ionic compounds. Making pottery involves forming ionic compounds. So making many types of pottery involves forming chemical bonds such as ionic bonds. Imagine that you are making a ceramic pot. You mix the clay, form it into a pot on a spinning wheel, let it dry, and then fire it in a kiln. When the completed pot cools, it is heat resistant, hard, and brittle. Why does pottery have these properties? As it turns out, pottery involves some amazing chemistry, beginning with the type of clay that is used. Clay can be rich in various compounds such as aluminum oxide, magnesium oxide, silicon dioxide, or zirconium dioxide. Some clays are rich in other minerals such as feldspar, which is a compound that contains potassium, aluminum, silicon, and oxygen. Microscopically, the clay particles are small plates surrounded by water. This structure allows the particles to move and be molded. When the clay is dry and fired, the water gets driven out, and ionic bonds form between the elements to form tightly packed crystals. The ionic bonds make pottery hard, but brittle, and heat resistant. So they're not going to melt when you put them in fire. And they're very hard, but yet they can still break, which is that brittleness. Ionic bonds form between metals and non-metals. Crystals of ionic bonds are found in many shapes and very pretty colors. Ionic compounds form from metals and nonmetals. The metals give up their valence electrons to the nonmetals to form metal cations and metal anions. So the metals are cations, which means what? They are positive. And did they gain or lose the electrons? They lost them. Anions are what charge? Negative. And what does that mean as far as gaining or losing electrons? They gained them. The metal cations and nonmetal anions form ionic compounds or salts and arrange into crystal lattices. Each crystal lattice has repeating units called formula units. So we talked about this already with the table salt in a previous lesson about the reason that it was a cube, or you get like these nice edges here, is because of the lining up positive, negative, in 3 dimensions. And that's going to be your crystal lattice. The formula units is just your formula. For example, table salt, 1 sodium for every 1 chlorine. An ionic bond is a very strong bond. In the ionic bond, the ions are attracted electrostatically. This attraction makes for a strong bond. We measure the strength of a bond by the energy required to break it. The heat energy required to break the bond is the same as that needed to form it. Okay, so think about sugar versus table salt. If you put sugar on a spoon and put it on the burner on your stove, what would happen to the sugar? It would boil and burn. If you do the same thing with table salt, what would happen? It would get hot, but that's about it. Because it doesn't take a lot of energy, relatively speaking, to break apart the sugar, but it takes a lot of energy to break apart that positive-negative electrostatic connection, that bond of ionic compounds. If you compare the bond energy of ionic compounds to those of covalent compounds, which are formed by sharing electrons, ionic bonds contain at least twice the energy of typical covalent bonds. Sugar is a covalent bond. Water is a covalent bond. Carbon dioxide. The strength of the ionic bond accounts for one of many of the properties of the ionic compounds. Ionic strength. And here you can see bond energy in kilojoules per mole. Kilojoules being the amount of energy, mole being the quantity. Like instead of saying a dozen, in chemistry they say a mole, which means a certain amount. So if you have table salt, it takes a little less than 1,000 kilojoules of energy per mole. And yet you can't do that on your stove, right? So that tells you how much energy this really is. And then look at magnesium oxide. It's crazy. It's almost 4 times as much as table salt. Whereas when you look at the covalent, they are all under 500. And that's why you can break them apart with the energy that your stove can produce. Ionic compounds have high melting points. Ionic compounds have high melting points compared to the elements that make them up. As an illustration, look at the ionic compounds in clay, particularly aluminum oxide and magnesium oxide. As you can see in the ionic melting activity, aluminum and magnesium have similar melting points. However, the melting points of aluminum oxide, so aluminum when it's in the compound, and magnesium oxide are at least 3 to 4 times higher. These high melting points make pottery very heat resistant, a feature that is obviously desirable for a coffee mug. But how can the high melting points be explained? Well, let's look at this first. All right, so here you can see boiling points and melting points. So aluminum boils at about 2,500 degrees Celsius, and it melts at about 750 degrees Celsius. Magnesium, pretty much the same melting point, but a much lower boiling point. Oxygen is less than 0. Okay, think about that. Oxygen in the air is in what form? It's a gas. So that means the air that you're breathing in already boiled. Okay, it's not liquid oxygen, it's not solid oxygen, which you can get. At about negative 220 degrees Celsius, you can get a solid chunk of oxygen, which is weird to think about, right? And you can get liquid oxygen. But that takes such extreme conditions that we don't normally have that on Earth. But it can happen, and we can force it to in labs, also by changing the pressure, which we'll get into later. Now, look at this. When you make them a compound, the temperatures raise dramatically. Not only for the boiling point, but the melting points. Look at that. That's like crazy. That's at least 4 times bigger for the melting point. So it really shows how when you make a compound, the properties are so much different than the individual, even the melting and boiling points. So why the high melting points? When a substance melts, the atoms become loosely associated or loosely attached. In ionic compounds, the strong ionic bond holds the atoms tightly in the crystal lattice. High amounts of energy are required to break those strong ionic bonds. Remember, it's a 3-dimensional thing. It makes a cube, so they're held together in like 6 different directions. The energy comes from heat energy, so more heat must be added in order to break up that crystal lattice. Thus, the ionic compounds melt at a higher temperature. So I just Googled ionic crystal lattice, and this is like the table salt one that we showed. And I like these two because it shows in the 3 dimensions. So if I look at this yellow one right here, this lithium, you can see that chlorine's pulling on it. This chlorine, that chlorine, that chlorine. And technically this one is and that one is. So it's getting pulled in literally all directions, which is going to hold it nice and tight. So it takes a lot of energy to pull apart all these beautifully structured bonds. Ionic compounds are hard and brittle. The ions in an ionic crystal lattice are tightly packed and held together by strong ionic bonds. This structure makes ionic crystals very hard, like a piece of pottery. For example, most minerals are hard ionic crystals. Similarly, when you fire pottery, ionic bonds form between the minerals and the ionic compounds in the clay, and pottery becomes hard. Ionic compounds are also brittle, and when a force is applied, it will break rather than bend. Sometimes I think people don't realize brittle technically means break instead of bend. So think of a candy cane, right? A candy cane is brittle. It's very hard, but when you break it, it's definitely going to break versus bend. Okay, assuming it's a candy cane that's already formed and hardened, okay? The ionic bond contributes to this property. The ionic crystal lattice is aligned positive ion to negative ion. When a force is applied, positive ions are pushed close to positive ions and negative ions close to negative ions. The electrostatic forces repel the similarly charged ions and cause the crystal structure to shatter along distinct planes. So when salt breaks, you're going to still get some really nice clean edges. So ionic crystals are brittle and break along regular planes. So of course when they're talking about planes, they're talking about like a vertical, diagonal, or horizontal plane. Use the magnifier to see how these different colored calcite crystals break. All right. So all right. Now some crystals are going to break just more cubic. Some are going to have more of an irregular structure, but still have the nice edges. Some definitely, you can see here, they're a lot smaller. So just kind of cool. Many ionic compounds readily dissolve in water. While heat must be applied to break the strong ionic bonds in a crystal lattice, it is possible to replace those electrostatic interactions with other ones. For example, water molecules are slightly charged, positively at one end and negatively at the other. So the reason for that is because when we do the Lewis dot diagram, it's easy to see hydrogen is full with 2 electrons. Oxygen, of course, needs 8 to fill its valence shell. And that's part of why we have the bend to the water molecule here, is because there's more electrons at this end. So we call that the partially negative end. And down here, it's partially positive. So it's not as straightforward as the sodium chloride, where sodium's positive, chlorine is negative, but it's just slightly more negative at this end, slightly more positive at that end. When an ionic crystal is placed in water, water molecules penetrate and surround the various ions in the crystal. The cations form electrostatic interactions with the negative ends of some water molecules, while the anions form electrostatic interactions with the positive ends of the other water molecules. The overall result is that the crystal lattice will separate and the ions surrounded by water, hydrous ions or aqueous ions, are free to move about in solution. So instead of being stuck in a rigid pattern, you can see here that the water just kind of surrounds it. And check this out. Here the chlorine's negative, so we have the positive hydrogens near it. Here we have the positive sodium, so we have the negative oxygen near it. So it spreads it out so that the salt is dissolved in the water. Ionic compounds conduct electricity. Consider this experiment. Take a beaker of water, place 2 electrodes in it, and hook up a power source. Then you place a voltmeter to measure the electric current that passed between the electrodes. Initially, there is little current in the water. Next, you dissolve sugar in the water. Do you get a current? Finally, you dissolve table salt in the water. Is there a current now? So, let's see what they have us do. So we have sugar. All right, so we have a battery, and we have our 2 electrodes, and they're in water, and this is a voltmeter. This is going to measure how many volts are in it, which is how much electricity. So we have our sugar in here, we have our salt in here, the same amount of each. It's dissolving, and what do you notice? The sugar, no change. The salt is conducting about how many volts? About 9 volts of electricity, which makes sense because that's a 9-volt battery. So 9 volts of electricity are going through this, just as if you would have the wires connected to each other. you will find that sugar, which is a covalent